Welcome back to Getting Started with Grasshopper. Today we'll build our first script following the Grasshopper design process, using everything we've learned so far about components and the interface. We will follow each step of the Grasshopper design process and begin by specifying what our outcome should look like. Let's say we want to create a model of a tower made of 3 sections, where each section has a different rotation. Our aim could be to set up a massing model where we can test different proportions and rotations. Before I show you the logic we're going to use, pause the video and take a minute to come up with a series of geometrical operations you would use to generate this form in Grasshopper. There are many different ways to create this form, and the one I will show you is just one of many. Here are the steps to build our script. We will start out by creating a circle. We will use the radius of this circle as the driver for the size of the tower's footprint. Next, we will divide this curve to get 4 points, and then connect them with the NURBS curve to create our base rectangle. Then we'll generate a surface from the curve. Once we have the surface, we'll move it vertically to 3 different heights. We're going to extrude the surfaces to create volumes. And finally, we're going to rotate each of the volumes by a different amount. Once the script is done, we can make adjustments at each of these steps to control and fine-tune our design. Let's switch to Grasshopper and turn this logic into components. Let's begin with our first step, a circle. Let's double-click onto the canvas and type circle to find a suitable component. The first result is a data container, but we want to create a circle to be able to adjust the radius with a slider from within Grasshopper, so that's not the component we want. Our next result says create a circle defined by base plane and radius. That's the one we want. Let's click on it to drop it on a canvas. The component has 2 inputs. The base plane of the circle, and the radius. When we hover over the inputs, we can see that both already have default values. The base plane is set to be the world XY plane, which is the origin of our horizontal ground plane in Rhino, and the radius has a default value of 1. Let's add a point container and reference a point from Rhino. This will be our base plane and will allow us to easily control the position of the tower. Let's create a point in Rhino first. Next, we type point into the search bar and add the component. Then right-click on it, select Set One Point, and finally select our point in Rhino. Now we can connect the point to the circle's base plane input. Technically, a point doesn't represent a base plane. A base plane is made of a point location as well as XY vectors that define a plane's direction. If we just provide a point, Grasshopper will convert the point into a plane and assume the default XY direction for the orientation. And that works for us in this exercise. Next, let's plug a number slider into the radius input to make it adjustable. Let's type number slider to add the component and change the range from 1 to 20. And set the slider accuracy to 1. Let's plug it into the radius input of the circle component. We can slide through the numbers and check in the preview if it works as expected. I will adjust the number to 10 for now. Next, let's use the divide curve component to add 4 points along the curve. Let's connect our circle to the first input, which is the curve to divide. We can see that the default 10 points have appeared on our curve. Now let's add another number slider to control the number of segments by typing 4 into the search bar. We get a slider with a range of 0 to 10 and the value set to 4. Next, we can connect it to the n input of the divide component, which defines the number of segments. The preview in the viewport looks good. Let's take a look at the outputs of the component. The first one contains the 4 division points. That's the one we're interested in. Next, let's create a NURBS curve. Let's type NURBS curve and drop it on a canvas. The inputs are the same as the interpolate component. The first input asks for vertices or control points of the curve. Let's connect our division points to this input. When we look at the viewport, we see that it's not quite what we had in mind. Let's see what's going on. First of all, we notice that the curve is smooth instead of simply connecting the points. This is because the default curve degree in the second input is 3. NURBS curves can have varying degrees, and this degree defines the relationship between the control points and the curve. If the curve degree is 1, which is called positional continuity, each segment from control point to control point is just touching, without any curvature. If the degree is 2, it means that the continuity is tangential. The curvature will be defined by the tangents of 2 adjoining curve segments. A NURBS curve of degree 3 blends the curvature across 3 control points at a time and appears the smoothest. In this case, we have curvature continuity. So if we want a polyline, we have to change the curve degree to 1. We could add a number slider once again, but since we're unlikely to change this value after setting it once, we can set the number inside the component directly by right-clicking on the curve degree input, going to Set Integer, changing the number to 1, and committing the change. Our preview looks good. The only problem now is that the curve is not closed. Last input defines whether the curve is periodic or not, or closed or not. The default is set to false, so let's change it to true. Once again, let's do this directly in a component, as we won't need to change this later. We right-click on the third input, go to Set Boolean, and change the value to true. Boolean is the term used to describe a value that is either true or false, or 1 or 0. We now have our base rectangle ready. Next, let's turn it into a surface by taking advantage of the automatic conversion functionality of the data containers. Since we have a closed planar curve, if we plug it into a surface container, Grasshopper will convert the curve into a surface. Let's type surface into the search bar and add the container component. Again, we have several outputs for the NURBS curve, but the output we need is the resulting NURBS curve. Let's plug it into the surface container. We can now see the shaded preview of the surface in the viewport. Let's switch to a perspective view to prepare for our next step, moving the surface to 3 different levels. Let's start with what we know. We need to move the surface, so let's search the Move component in the search bar and click on it. There are 2 inputs, the geometry to move and the translation vector. If we plug the surface container output into the geometry input of the Move component, we can see that the surface is already moved up. This is because, once again, there is a default vector inside the translation vector input. A vector with 0 in the x-axis, 0 in the y-axis, and 10 in the z-axis, which points upwards, as we can see in this little widget in the viewport. By definition, a vector is made of a direction and a length. We know that we want to move the surface up, which is the z direction. So let's begin by adding a z vector to lock the direction of the translation. If we just type z into the search bar, the first result will give us a unit z base vector that we can use. Let's connect it to the translation vector input of the Move component. The update in the viewport shows that the surface is now moved much lower. That's because the unit z component also has a default value, this time of 1. We can define the length of our translation vector by plugging a number into the factor input of the z-unit component. Once we do that, we have defined both the direction and the length of our vector. If we want to move our surface up to 3 different levels, we need to feed 3 different vectors into the translation input of our Move component. We could add 3 sliders and plug them all into the F input to generate the 3 vectors, but since we want each of the segments of our tower to be the same height, we can use a component called series. As the name suggests, this component creates a series of numbers. By checking the inputs, we can see that it needs the starting number of the series, 0 in our case, the step size for each successive number, and the count of the numbers to generate. Let's add 2 sliders, one to define the step size and one to define the count. We can leave the start of the series at the default value of 0. Let's type 20 into the search bar and hit enter to add a number slider with a range from 0 to 100 and the value 20. And let's do the same again with a value of 3. Let's connect the number sliders to the series component. Let's add a panel component to see the output of the series component and check whether the number series looks the way we want. We can see that the numbers are what we expect them to be. The series starts at 0, has a step size of 20, and contains 3 numbers total. Nothing has changed yet in our preview because we still need to connect the resulting series of numbers to the vector input of our z vector. As soon as we do that, we can see our 3 resulting surfaces in the viewport. If we select the move component, the surfaces are highlighted in the viewport. The first surface has been moved by a factor of 0 along the z-axis, so it is still on our base plane. Now let's extrude our surfaces next. Let's drop an extrude component onto the canvas and check its inputs. The extrude component can extrude both curves and surfaces, and needs an extrusion direction in form of a vector. Let's already connect our moved surfaces. Nothing happened in the viewport because the extrusion direction input has no default value. Let's set up the extrusion direction, which is once more z, or up. So let's add another z-unit component and connect it. We want to extrude the surfaces up by the same amount as the distance between the moved surfaces, which is 20. We could add another slider and give it a value of 20, but if we were to change the step value of our series later, we would need to also manually change this extrusion height. Instead, we connect the same numbers ladder we used to define the step size with our vector input of the z value for the extrusion. This way, the 2 values will always be linked. Perfect, we have our 3 extruded segments. The last step is to rotate the extrusions. Let's add a rotate component. Let's find the right component for the job. If we type rotate into the search bar, we get many results. Grasshopper has many components that can help us rotate objects, and they're all slightly different. Let's carefully read the pop-up description to pick the right one. We want to rotate an object in a plane. It's the first result. Let's select it. Let's check the inputs. The first input is the geometry to be rotated. The second one, the rotation angle. It's important to note that the angle input must be in radians and not degrees. Luckily, we can convert degrees to radians easily. I'll show you how in a bit. There's already a default value in here, 0.5 times pi, which is the radians equivalent of 90 degrees. The last input is the rotation plane. When we rotate an object in a plane, the rotation plane is the point around which the geometry is rotated. Let's begin by connecting our extruded volumes to the geometry input of the rotate component. If we check in our viewport, we now have what looks like a copy of our tower in what seems a random place. The reason is simple. Let's go to the top view. Since we haven't specified a rotation plane yet, the default is still the world XY plane, which is the origin. Together with the default rotation of 90 degrees, we can see that the component took our input geometry and simply rotated it 90 degrees around the origin. Let's specify the rotation plane to fix it. I will head back to the perspective view. Just like with the base plane for our circle, we can specify the base plane with a point. We want the rotation point for each segment to be the center point of the segment. I will activate this isolate preview command and click through the components. I want to take a look at the moved surfaces only. We want the rotation to happen around the center of each of these surfaces. To find the center point of a curve or surface, we can use the area component. Let's add an area component to our canvas and check out its inputs and outputs. It accepts closed curves and surfaces, basically any planar geometry as an input. The first output is the area, a number, and the second one is the centroid, the center of our geometry. Let's plug our moved surfaces output into the area component. When I select both, we can see the surfaces and the corresponding center points. Let's turn the isolate preview mode back off and connect the center points, the second input. we can hover over it to make sure, to the base plane input of our rotate component. If we now select our rotate component, we can see that the preview lights up on top of our existing extrusions. The base plane is now where we want it. The geometry is actually rotated by the default 90 degrees, but we can't tell because we're dealing with a square. Next, let's add a number slider with a value of 45 by typing 45 into the search bar and hitting enter. This will be our rotation angle in degrees. To convert it to radians, we need a component that converts degrees to radians. It's simply called radians. Let's find it in the search bar. We can see from the description what it does. It converts an angle specified in degrees to radians. Let's connect the number slider to the degree input, and then the resulting radians angle to the angle input of the rotate component. We can see the rotated tower segments in our Rhino viewport. There's some overlay going on in the preview. Since we haven't turned off any preview so far, all the geometries we've generated so far are visible at the same time. We're seeing the extruded volumes as well as the rotated volumes. This is because effectively all of them exist within the script. Let's turn off the preview of the extrusions so we just see our rotated segments. Let's click on the extrude component, check in the viewport if it's the component we want to disable the preview for, and then hit Ctrl-Q to turn off the preview or right-click on it and toggle preview. We can see the moved surfaces still peek through, so let's turn off the preview of those as well. So, our rotation is set up, but at the moment all segments are rotated by the same amount. If we want to rotate each segment differently, we need to provide 3 different angles, one for each segment. Let's use the series component once more to create a series of numbers. Instead of creating a new series component, let's copy the existing one by dragging it and tapping Alt once before letting go. We can keep the default starting value of the series of 0, and also the count, which should match the number of segments we create with the other series component. But we want to be able to change the value of the angle, so let's copy this slider and replace the step size input. We can now connect the output of this number series to our degree input of the radians component, which feeds into the rotation angle input of the rotate component. We can delete our old slider. You completed your first Grasshopper script. We can now go back and change the values at every step of the command sequence to tweak our design. By changing the radius of the circle, we can change the overall footprint of the tower. The number of divisions defines the shape of our tower segments. The value of 3 will give us a triangular outline, and 6 a hexagonal shape, and so on. We can then adjust the height of the tower segments, the count, and the rotation with these inputs. To reach this result, we don't have to start with a point. We could reference a circle in Rhino instead of creating it in Grasshopper, or start the script with a referenced surface from Rhino. The starting point of our Grasshopper script depends on the degree to which we want to be able to change parameters. If we are only interested in being able to adjust the rotation, we could start the script with the extruded volumes. In our example, we have complete control from the location of the tower to the final rotation. Once we're happy with the result, we can bake it by right-clicking the final component and selecting Bake. At this stage, we can turn off the Grasshopper preview by selecting this first preview mode button and continue our work in Rhino. This was the last video lesson of this mini-course. You now have a firm grasp of the Grasshopper interface. You know how to put together a script, and you know your way around some of the key components. Here's some good news. If you've made it this far, it shows that you have what it takes to master Grasshopper. You have the discipline needed to keep learning consistently. Tomorrow you'll get a final small design assignment. Use it to practice and test your understanding of what you've learned so far. I'll see you there.